Welcome to Pratidhwani, where we try to humanize science. I'm your host, GV Pawan Kumar. It is my delight, pleasure, and an honor to welcome the guest on this episode, Professor Aninda Sinha. Aninda is an outstanding theoretical physicist who has kind of widely contributed to various questions related to superstring theory and also various different areas within theoretical physics. In recent years, he has also been involved in very interesting research related to quantum field theory and superstring theory. And more recently, there has been some very fascinating findings from his research group, where they have been able to come up with a very interesting series on the uh, pi. The pi, as in the pi, what we are aware of in mathematics, all the way which goes back. And what is more fascinating is it connects to the Madava series in a very interesting way. And Aninda's work actually has generalized that particular series, so to speak. He also has been involved in various different kind of questions related to entanglement entropy and bootstrap kind of formalism and other related questions in theoretical physics. He also is a decorated scientist. He has won numerous awards. But he's also an excellent teacher. I had pleasure of listening to Aninda when he visited ISA Pune a while ago, and his talk on that particular series was indeed very fascinating. So, with this brief introduction, I welcome Aninda on Pratidhwani.
Thank you, Pavan. It's great to be talking to you, and you're doing a wonderful job. I listened to some of your recordings, and they are very inspirational.
Yeah. My pleasure. Absolutely, my pleasure. Aninda, please give us a gist about your origins. Where were you born, and what were the kind of upbringing you had growing up?
So I was born in Calcutta. I grew up in Calcutta, so I did my schooling in Don Bosco. I had a very uneventful upbringing because my parents were very sheltered me a lot. So my father was a well-known political figure, although he was a very well-known I mean, he was an academic in the sense that I actually come from a family which places a tremendous amount of emphasis on academia. So my grandfather was the land reforms minister of the first ever Bengal government post independence, and he was actually instrumental in the zamindari abolition. And then my father took that up, and he was involved in politics for a very long time. He was also a member of parliament between 1984 and 1989.
Oh, could you please name him? Okay.
His name is his name was Satish Chandra Sinha. So
Ah,
he died in 2010. Um, and so my grandfather was a very well-known economist of his times, and he did very well in studies and so on. So when we grew up, we got to know about our family history. So the pressure was always there that we have to contribute something back to society because we came from some kind of, in a sense, a privileged background. So that kind of pressure was always there that we have to give back something. My uncle was also a well-known physicist. He passed away last year. He was Professor Bikash Sinha, who
yeah,
was
yes.
director of the Shah Institute of Nuclear Physics for a very long time, and BCC. So I grew up essentially being surrounded by people who were well-known figures. And so, in some sense, I wanted to establish my own identity. So that's why I think uh, it brought about some kind of a competitive streak in me to do well in academics. Of course, I wanted to play cricket, but my father didn't let me. So,
So much of a story of every boy growing up during that time.
yes, indeed. So I did my schooling in Don Bosco in Park Circus in Calcutta, and I had basically very good teachers while growing up. I think it's like every growing when you grow up in a sort of a sheltered environment in a sort of a good school, you have I have similar kind of upbringings. typically have good friends, and then you start discussing with them, and then that's how essentially it was with me as well. I did my undergraduate in Jadavpur University, so BSc was from 96 to 99. And then I followed my father's and my uncle's footsteps, and went to England. So my father had done his diploma in geophysics from Imperial College London. So that was the equivalent for equivalent to a master's during those days. That was many years back in 1959. And so I had asked my father, why did you do geophysics? Because his interest was clearly in physics. And he said that, because my grandfather apparently told him that there's a lot of opportunity there, so he did what his father had said. So of course I did no such thing. My father actually, if initially tried to discourage me from going into pure sciences because of the fact that there was no money in it. And but then when he saw that I was very interested in pure science, he was extremely encouraging and supportive. Um, yeah, so I went to Cambridge for my undergraduate. So that was in 1999. And then I was in Cambridge till 2007. I did my master's there, I did my PhD there, and I was also a fellow of Gonville and Keyes College for 3 years. Yeah, that's
Fabulous, fabulous. We'll come to each part as we go along the conversation. Tell us a little bit about your influences and how was it growing up at your home. I would also want to know a little bit more about the experience at Don Bosco because it's a kind of a reputed school.
yeah.
But before that, we just give us a gist about the kind of environment in which you grew up. How was it at home?
So
And
it was a very sheltered environment because my mother was a homemaker, and so basically she made sure that we didn't do anything out of we didn't monkey around too much. Let's put it that way. So yeah, of course, it wasn't as if that we were being forced to sit down to study at a particular time and so on. I mean, I think. I distinctly remember that when I was around grade six, I got hold of my grandfather's diary. So my grandfather used to maintain diaries in beautiful handwriting, and I found out from those diaries that my father actually tried to copy his handwriting because it was so beautiful. So my father also had a beautiful handwriting and so on, and there were statements in the diary which sort of spurred me on a lot because it was generic statements when he was growing up as a student, and because he did a degree in economics, so he had a background in economics, my grandfather. And I think it was that phase where I thought that I have to do better than what I was doing at that point of time. So yeah, and my father was traveling a lot, so it was because of his work. His constituency was in our ancestral home, which was in Murshidabad in Kandi. And so he was basically during the year around 6 months of the time he was there. So it was essentially my mother who made sure that things were maintained at home. I have a sister who's also a doctor, who's a doctor. She's a doctor in PGI Chandigarh.
Oh, okay.
So both of us sort of grew up together till around when I was in class 10, because then she moved to do her MBBS. Yeah, so I had good friends, a good circle of friends who I've maintained contact with. So yeah, I would say that I come from a privileged background, and the onus was always to give back to society in some form or the other. Um, yeah, so that was it basically. Um,
Wonderful, wonderful. So, one of the things I would want to also kind of ask is during this early phase, was there also some kind of an influence which probably kind of made
uh-huh.
you
Right.
attracted towards
Yes.
physics and things like that? Yeah.
Right. Yeah. So in school in Don Bosco, we from class seven, we had a very good maths teacher by the name of Mr. Dias,
Mm.
and he was extremely encouraging. And when he saw that I was very interested in mathematics, he sort of took me under his wing, so to speak. And what is beautiful about that phase, I remember, is that we learned all these theorems from Holland Stevens's classic textbook on geometry, and I was very fascinated by the axiomatic development, starting with Euclid's axioms, that you could actually build on so many things in two-dimensional geometry. And I think Mr. Dice's influence actually got me very, very interested in mathematics, and I was never scared of mathematics from there. So I would actually name him. And then being in Don Bosco, of course, was one of the elite schools in Calcutta. So we had the privilege of having some wonderful teachers who were very good human beings. I mean, it's not as if they came to class, lectured, and then went away. They also encouraged me to sort of think beyond. Um, and so while growing up in, I think it was class 10, where we started having this very well-known teacher in the math circle in Calcutta by the name of Mr. Patrose.
Mm.
So Mr. Patrose was legendary enough that other schools students also took tuition from him. I never took tuition from him, but he was of that kind. You know, he would be very jovial, and he would give very advanced problems, not in the curriculum, because it was the ICSE and ISC curriculum that we followed. Um, but he would give many more advanced topics. He would discuss many more advanced topics than what was followed there. So, in fact, he used to have the habit of having these surprise tests where he would come with a sheet of questions, and and those questions, and he would give us probably 10 minutes or 15 minutes within which we were supposed to do. And it was not unusual for people to do really badly in those tests.
Mm.
So there was one distinct memory that I have where in one of those tests, the entire class got zeros. Okay, so including me, I also got a zero because it was that difficult. And it was a part of life. So we actually started to also realize that failure was a part of growing up. And so we took it in our strides, and we had a good time laughing. So how much did you get? Zero. So how much do you get? So and so yeah, so it's those kind of memories which I think somehow live on with you. But I do remember that these exam pressure was of that kind that even after so many years, 30 years after I finished schooling, I still have this one recurring nightmare where I still have cold sweats thinking that and this is the dream that I have, that I've entered an examination hall and have prepared the wrong subject.
Yes, yes.
So this is a pressure. I don't know how many, whether you also have similar kind of experiences where you wake up thinking that you have an exam to take tomorrow and you're not prepared. So, this
Yes.
is a negative part of the exam pressure that we grew up in.
Mm. Yep.
I think too much was made out of this being having to do well.
Mm.
And I think the fact is that research and examinations and coursework, they are different things. And
Yes.
this you get to learn only when you start doing research. Till you actually start doing research in PhD, you actually don't realize that following a textbook, working out the problems is not the same thing as actually coming up and designing a problem of your own. So this is something that actually is not emphasized enough in our education system, which hopefully in the foreseeable future is going to be set right, I guess, as far as I can see, because as you know, we have a daughter who's 13
Mm.
years old, and we are seeing her growing up, and thankfully she does not have the same kind of pressure that I had to go through.
Mm.
But I think there's some genetic programming where she thinks that she has to do well as well.
Yeah.
So these kind of things hopefully will change for the better in the foreseeable future.
Yeah, wonderful. In fact, you mentioned a very important point about the fact that answering a specific question which is already defined is so very different from really coming up with a question.
Exactly.
In fact, this even just reminds me the morning where I taught a class and I was just mentioning the same issue, and it's such a critical aspect of doing anything which actually is slightly more impactful. You would have to define the problem in its clarity.
Yeah.
So, in it looks also that you were exposed to a very good quality teaching especially in the context of mathematics. In fact,
Yes.
that is something I really want to emphasize, Ninda, because from whatever I can understand, the work what you do involves quite a bit of involved mathematics, but also brings in beautiful physics with that.
Right.
And it's because the way physicists look at mathematics is different from, let's say, somebody who is growing up doing only mathematics,
Right.
because one will have to utilize mathematics as a tool, and
Exactly.
certain times it is also a surprise of the mathematics itself actually can become a kind of a formulation for physics, which has happened extensively in various different theories, in string theory especially, and it has a very rich history. Tell us a little bit about that kind of training part of you becoming a theoretical physicist with strong foundations in mathematics, because that is an important question. A lot of students, including researchers like us, would be interested in knowing that. Yeah.
Right. I think the way that Indian education system, and especially where I grew up, because I did my undergraduate in Jadavpur University, so the experimental facilities in Jadavpur University during those times, 96 to 99, were abysmal. I
Mhm.
mean, so we were doing some archaic primitive experiments like Cater's pendulum, where, there's this rod with
Yeah.
various
Yeah.
holes in it, with rust in them, and then you're supposed to hang it through some nail on the wall, and then
Yes. Yes. Yes.
by hand you're supposed to plot a curve, and that curve is supposed to be some kind of a parabola, and it is never a parabola, and so you eyeball and try to see what you get, and then after doing a lot of hard work you get 10 as the answer for acceleration with 9.8, and then the examiner actually tells you, why didn't you get 9.8? And of course, I had a very good teacher at that point of time as well, in those days, and he actually explained to me that the question wasn't targeted to saying that, oh, your experiment was bad, but then you have to explain why you didn't
Yeah.
get 9.8. And then of course, at that point of time I hadn't thought too much about it, but then he pointed out, if you observe the rod very closely, there's supposed to be rust in those
Uh-huh.
holes, so you're supposed to take a sandpaper and make it smoother so that
Yeah.
the frictions effect is not that much. And so these kind of things, while on one hand it was okay, but on the other hand they were so primitive
Mm.
that, for example, when I went to Cambridge to sort of do the masters, my director of studies, Professor Richard Hills, he told me to actually go and look at some of the experiments that Cavendish was doing in the second year undergraduate.
Yeah.
So I entered this big, huge lab, and at that point of time, these students were doing water wave measurements. And so there were these large tanks of water, and then there were paddles in them, and it was motorized. It wasn't as if they were doing by hand. So there was some motor, and they could actually tune the frequency with which the
Uh-huh.
paddles were moving.
Yeah.
And the output was measured in some clever way, which I've forgotten, maybe using acoustics or something. And
Uh-huh.
it was automated. So the readings were automated, and it was connected to a computer, and I was just blown away because I'd never seen these interfaces between these automated ways of taking readings. And so I went and told my DOS, director of studies, that retraining myself as an experimentalist is really too hard. But because of my education in Jadavpur University, we actually were exposed to some very good courses in mathematical physics,
Mhm.
and I was really very interested in mathematical physics. So there were two courses in mathematical physics, essentially covering, I would say, the whole of Arfken and Weber.
Weber. Okay. Very
Arfken and
nice.
Weber, and so in fact, the second course in mathematical physics, which was taught by Professor Gananjun Nag,
Mhm.
he set a competition. So he actually told us to basically use the method of spherical harmonics to compute the energy levels of a nucleus.
Wow. Nice. Nice.
And that was set as a challenge, and I was able to do it. And it was a competition, so whoever submitted it first and got it right, he would get a prize.
Uh,
So I managed. I took it as a challenge. I managed to solve it. I got the prize, and he gave me the book called Men of Mathematics by Bell.
Bell.
Uh,
E.T. Bell. E.T. Bell. Yeah.
E.T. Bell's book, and that book had the background of several great mathematicians, Galois,
Yes. Yes.
and others. And Galois' story, as you know, is remarkable.
Yeah. Yeah.
That he died in a duel, and
Yeah.
and he invented a whole area of mathematics by the age of 20. And so, these kind of things were very encouraging, at least so far as mathematical physics is concerned.
Mhm.
Our courses were mainly theoretical. So the exposure that we had in something like electronics was also theoretical. So we were sort of solving
Mhm.
electrical circuits as a maths problem, not really going and making things in a lab.
Yeah.
So the whole thing was that we were sort of did not have much exposure to hands-on activity. And this is a very bad thing, in my opinion, in the undergraduate education system that we have. In fact, it is still prevailing that we are not encouraged to do things hands-on. And
Right.
this is to sort of quote Feynman. I don't know whether you know the story that Feynman was once asked that, why I don't know who asked it, but then he was asked why are Japanese people so inventive, and whereas Indians are not. And then sort of he reflected on this and he said that maybe it's because of the culture, because in India we have this culture that if we have a bulb to replace, we actually call the electrician, we don't do it ourselves. We are too scared to open an apparatus ourselves and fiddle around and figure out whether what needs replacement. So now we have urban company to sort of ruin our.
Yeah, so correct. Yeah.
So, so these kind of things are not really encouraged.
Encouraged, yeah.
Yeah, so this is, I think, the reason why at least I was programmed to be a mathematical physicist, sort of because of the exposure that I had. And when I went to Cambridge, the exposure was equally sort of in that direction, because we had two courses in theoretical physics. So I did part two physics in the Cavendish labs, and then I did part three maths.
Uh-huh.
And so the part two physics course had two theoretical physics components. These were electives, so it's not necessary that you had to do theoretical physics, you could do something else as well. And the first course in theoretical physics was taught by Professor Eugene Terenchev. I don't know where he is currently, but the second course, I guess you'd know the name of this person, Professor Peter Littlewood taught us.
Littlewood.
Yeah,
Wow.
Peter
Okay.
Wood taught
Yeah.
us theoretical physics too, and both were fantastic. I really enjoyed them a lot, and I sort of aced them. So I
Uh-huh.
knew that I was meant to do mathematical physics, I guess. So this was my.
Fabulous. Fabulous, fabulous. So, because we are talking about your kind of upbringing and kind of getting exposed to advanced mathematics as a undergraduate and also a PhD student, what was the broad learning, Aninda? Like, if somebody wants to, let's say, get into that stream of kind of research, and there are many, because a lot of Indian students, including, for example, at ICER, there are many students who are deeply interested in theoretical physics. What
Yeah.
is that you would encourage them to do, especially at this particular stage where they're like doing their BSc and MSc at that particular level, or even beginning of their PhD? What
So
is the
there are
kind
two
of broad
things.
thing? Yeah.
So let me tell you what I had encountered and how things have
Yes.
evolved since
Ye-
then.
Yes,
So,
please. Yeah.
so our courses did a lot of vector calculus. So we did. I think the book that we followed was Murray Spiegel's book.
Yeah. Yeah.
It's a beautiful book. I mean, all these Schramm series books are quite nice anyway.
Very nice. Absolutely. Absolutely. Yeah.
And then there were these courses on special functions, spherical harmonics, and sort of orthogonal polynomials, waves, those kind of things. Um, and one thing that was not taught, and I think depending on where you are, it's not really taught in depth, is complex analysis.
Mm,
So, calculus of residues, complex analysis, and subtleties behind various applications of various theorems in complex analysis. So, this is something that is not really uh, emphasized enough at the undergraduate level. I think in IISc we do have courses in mathematical physics, and complex analysis is a part of it. It's a very small part, complex variables we call it.
variables. Yeah.
And I think people should start getting exposure to complex variables at an early stage, because there is a very important difference between real variables and complex variables. So you can actually do things that you cannot imagine doing using real variables. So, for example, analytic continuation to make sense of infinite series. These are very important because the simplest geometric series that we encounter, 1 plus x square and so on, which is 1 over 1 minus x, is the simplest
Correct.
example of analytic continuation, because you can put x to be whatever you want in that final formula, But if you actually put x equal to 2 in that original series, it diverges.
Diverges, absolutely.
But
Yeah,
1 over 1 minus x does not diverge if you put x equal to 2. So,
nice.
so what that means and why you are allowed to make sense of it, these are things that play a vital role in theoretical physics. So, for example, if you calculate the Casimir energy between two plates,
Plates, yeah,
you
yeah,
take into account the vacuum energy, then you have to do regularizations of this kind where you are supposed to make sense of analytic continuation.
yeah, yeah.
The other thing that has changed, apart from the fact that we did not learn complex variables as well as we would have liked, the other thing that has changed over the last several years, over the last couple of decades, is the availability of computer algebra packages. So, when I teach mathematical physics, I actually teach them through this software called Mathematica because it
Nice.
helps us visualize a lot of things that otherwise would be very complicated. So, for example, the analytic structure of a function can be beautifully visualized in Mathematica. So, I think to standardize undergraduate education, one should sort of teach the usage of these modern computer packages, computer algebra packages, at a very early stage. Because I see students who come to work with me for an undergraduate or summer undergraduate project or summer project or from various places in India, and they have had very little exposure to these kind of softwares. And why these are very important is because the emphasis is not on manipulation anymore, because the computer's package does that. The emphasis is on understanding the concepts, and
Concepts.
you can focus on the concepts and let the computer algebra package do the manipulation for you. So it's very important to be aware of these kind of things because right now there is very little to gain by remembering the recursion relations that say the Legendre polynomials satisfy, because those are documented somewhere, and there are inbuilt things in Mathematica that enables you to simplify these kind of things. So because of this, I think one can get a lot more mileage if you used computer algebra packages in your research at a very early stage, because the students who manage to write papers in undergraduate typically do something which has got a very hard numerical component.
Yes,
And that's always key things. You can do so many things in mathematics. You can do image analysis. You can
yes,
singular
yes.
value decomposition. You can just feed in the image as an object, and you can actually compress it. You can learn beautiful things, complicated concepts, if you had this kind of an exposure.
Beautiful, beautiful. That's such an important point what you're mentioning, because this there is a notion among a lot of students, especially while growing up, and I can understand because there would be some lack of exposure. Because it is always nice, of course, to really do the pen and paper stuff. It is which is always there is some kind of romantic aspect of that notion of doing things. But you very correctly mentioned that. It is just like you building on the available tools, because you can actually go to a higher plane to really ask questions which are of different kind.
Right.
And that is something which is very important. What you're mentioning is so critical, and that actually applies across physics. In fact,
Yes.
that's something which is very important. But while growing, were you also exposed to these kind of the packages and softwares which
Much
you
later,
use?
actually,
Much
much later.
later,
So
probably. Yeah,
I
yeah.
had we had a sort of a young teacher who had just come back from the US. His name
Uh-huh.
was Professor Shubhankar Ray.
Yeah.
I wonder whether he's still in JU or not. But he is the first person who actually talked about Mathematica, and he held a couple of evening sessions after
Nice.
college sessions, exposing us that you can do so many things more. And there it was some primitive version of Mathematica, like Mathematica 2.0 or something,
Yeah.
but he was showing us how to solve wave equations and sort plot these beautiful curves, graphs that we always thought that you had to take a graph paper and then
Yeah.
plot points and plot graphs by hand, which was never the case.
Absolutely. In fact, since you mentioned about complex analysis, in fact, that's one of the things which is extensively used across physics,
Yeah.
even in engineering, for that
Yes,
matter.
exactly.
As
The Fourier analysis, for
for an
example.
analysis, exactly. And there, the concept of imaginary numbers,
Yeah,
when it comes to visualization, these are all tools which are extensively important. And
exactly.
I'm very glad that you actually mentioning, because. it has to come from the horse mouth, so to speak, because a person who is really, involved in higher order kind of theoretical physics and mathematical physics, to tell this is also a kind of very very important notion to understand. And
Yeah.
so going further, were there also some influential books you really studied during that early phase, which also kind of kept your interest high, both in terms of technical aspects and also kind of general inclination towards science?
Um, at the undergraduate level, I guess maybe I could mention Mr. Tompkins in Wonderland
Ah,
and the Feynman lecture series.
let's,
But
yeah,
to be very honest, the Feynman lecture series, we all hear that these are all great books and so on.
yeah, yeah.
But I always found the Feynman lecture series difficult. So
Mhm.
I did not find it like many people say that their eyes were opened after reading
Yeah.
Feynman's. That didn't happen to me at least, because I think Feynman's physics intuition was a bit higher levels of our.
Higher, yeah, yeah, yeah.
And of course, he has many interesting examples. He teaches quantum mechanics in his lectures in a sort of a very different way.
Different way. Absolutely, absolutely. You're absolutely correct. In fact, volume three is very, very unconventional way of looking at quantum mechanics. You're right.
Yeah.
Yeah. Yeah.
Yeah, so we were actually told to, because of the kind of teachers that we had, the book on quantum mechanics that we were recommended was this book by Cohen Tanauji.
Taroji, yes,
Yeah.
yes, yeah.
And that was very sort of down to earth. It had this philosophy: shut up and calculate. And
Yes, yes,
that, at least when you're learning quantum mechanics, I think that is the best approach to take. As you grow older, you realize and you hear Penrose and you hear what the other great minds, Tony Leggett and others,
yeah.
who have been actually saying, even Gerard Tooft, who have been saying that quantum mechanics has to be replaced by something more fundamental. This is a sentiment that was echoed by Dirac many, many times. So Dirac, who is one of my heroes, actually, uh, he sort of abhorred the way that quantum field theory was done. So, but these kind of experiences I had was later on, not really during my undergraduate days. In undergraduate days, I was basically very heavily influenced by my undergraduate mentor, Professor Soumitra Sengupta, who was
Mhm.
SSG, as we used to refer to our teachers by the initials.
Initials, yeah.
SSG, NB. So NB was Narayan Banerjee, who taught us relativity when we were growing up. So these are very influential teachers, at least in my mind, because a teacher who actually comes across as somebody who knows his topic inside out, who actually also openly admits that I don't know this,
Mm,
they have a huge influence because you, first of all, you sort of want to be like them in some sense, but
mm.
also you realize that it is not important to know everything.
Absolutely.
And this is something that I now that I look back, I feel that it's because of this. I always tell my students, whoever comes to work with me, that be aware that I'm going to learn from you. Don't expect that I'm going to provide you guidance. So I'm
Nice,
going to give you
nice.
some broad direction, and we are going to explore together. So those and most of my students, and thankfully I've been very lucky here in IISc. All my students have been very forgiving because I don't pretend to know everything. In fact, I probably know less than half of what I pretend to do. So it's very important that you have students who go on a journey with you, and this is something that we learned from these kind of mentors that I had, especially SSG, who was an older brother to me at that point of time. So it's important to come across these people because they are great human beings. They're very helpful, and then you realize that you can do physics also.
Good.
Um, and then when you go to Cambridge and you do part two, and then you get lectured by the inventor of string theory,
Yeah.
and you see Stephen Hawking in Damped. You see Freeman Dyson coming and giving the Dirac lectures. That actually teaches you a lesson in humility because
Great.
you can't go and boast that, oh, look, I can do this. Nobody cares because the moment you turn to another corridor, you see some stalwart there,
Yeah.
maybe John Coates or somebody like that, who's there, who's a famous number theorist, and uh, yeah, it actually teaches you a very vital lesson in humility that you can strive, you can hope to accomplish, but there's no guarantee. So
Beautifully put. Beautifully put. In fact, that is actually also a hallmark of scholarship, so to speak. I'm so glad you actually are telling this uh, because there is also a saying in Kannada to translate it. The pot which actually is completely full usually doesn't spill the water out because it's only the one which is empty which actually keeps actually is spilling it out. But this is something which is very fascinating because you are also getting exposed to new questions in your
yes,
field. Because I assume if you're really talking and also interacting with people who are who's who in your field, you also are getting exposed to the forefronts and the cutting edge in your field. And what was your experience, Aninda, having come from Jadavpur University, going into a new environment? Of course, you are very well prepared to that particular experience as a student. But as a researcher, these are all new experiences for you, right? Because you're really getting exposed. How did you feel? For example, the names you really mentioned are absolute stalwarts. But there's also a great culture there of being irreverent and also open to kind of interaction, etc. So tell us a
yeah.
little bit about that
Okay,
experience you had.
so let me tell you about sharing an anecdote. When I
Yeah.
started PhD, so I did my PhD with Michael Green, who
Yes.
was one of the inventors of modern string theory. And
Yes. Yes.
the first meeting that I had with him after joining him as a graduate student was he defined for me who the ideal student in his eyes is. So he told me,
Uh,
according to me, an ideal student is one who goes and finds his own problem and solves it. So I read between the lines, footnote, don't bother me. Okay, so so you're expected to go read around, define your own problem, and you should be able to define a problem. Maybe he'll suggest some broad direction, and that was the typical Cambridge culture that they define some vague direction.
yeah. Yeah.
I have to use the words vague because it's not really that. In theoretical physics, there are very very few people who actually know point A to point B. We are actually
Yeah.
we are doing random walk in between, and we'll be very lucky. We know the starting point that we here is where we start, and we have some vague direction that we want to solve. We want to understand the black hole information paradox, or we want to understand something which stretches the boundary of theoretical physics. Okay, but there's no guarantee that you're going to reach that. You're going to do some random walk, and then maybe you'll reach somewhere interesting. It might be completely something completely different. And this is something that people don't tell you when you
Uh,
start doing a PhD. Okay, they'll define some problem, and the first problem that was assigned to me was a notoriously difficult problem, which I had no idea how hard it was. So he told me to calculate the two-loop four-graviton scattering amplitude in type 2 string theory. So I said,
okay.
fine. It's a great opportunity. I'm going to learn something about string theory this way. So I said, okay, I'm going to do it. And then as I delved into the subject, I started reading literature. I realized that the amount of technology that one had to learn to solve this problem was really, really sort of, and it's beyond super exponentially hard. Okay. And I was extremely lucky because within 2 months of starting my PhD, this problem was solved by two established researcher by writing four papers, which totaled to 100 pages. So they wrote four different papers, and the solution actually took 100 pages. And when I started working on this problem, Michael's reaction was that, oh, if you manage to solve this problem, this will be a very good first year report. And so this was he never told me that this is a very hard problem. Be aware, it might take you some nothing like that. Yeah, this if you manage to solve it, it will be a very good first year report. So so they hide the fact, the difficulty level. So that's a great way of going, of
Yeah.
course.
Yeah.
But then the danger is that you falter and you stumble on your own. So
Yeah.
that is the Cambridge culture, that you try to find your own way. You learn to swim or sink on your own.
Mhm.
If you learn to swim, great. They will
Yeah.
be as supportive as possible. They will be behind you. But if you sink, it's up to you. So that's your problem. That's not their headache. Yeah.
Wonderful. Wonderful. Very, very interesting kind of experience. So how did it go?
I learned how to swim, of course, and I had to. I learned how to swim basically by realizing that one, Michael's problems were super tough, and only he and maybe two other people in the world were interested in the solutions. So I had to sort of know what most groups, research groups, were interested in, and so I had to try and define problems or talk to postdocs or basically form a team with younger students and sort of similar age students and try to do something. And that's what we did. And so during my PhD, there was one particular problem that we landed up solving, which needed us to invent a new kind of function. So we invented a version of the gamma function. So
Uh-huh.
my association with the gamma function is long, and
Long ago.
yes,
Nice, nice.
but we invented
Wonderful.
a version of the gamma function which had a branch cut. So
Uh-huh.
usually gamma function has a pole, but
Uh-huh.
this was a gamma function with a branch cut, and the size of the cut actually had a physical interpretation. So it was like the size of an electromagnetic field. So how strong that electromagnetic field is. There's a version of that field in string theory, but it's not quite the electromagnetic field, something like that. So there's a physical interpretation to that to what that meant. And so when we because of the fact that this is where I think ignorance also helps, because if you read around too much and if you are extremely aware of whatever is trendy and hot, you will try to subconsciously mimic that. Whereas if there is a balance, then you might be trying to invent your own way.
Mm.
You might be trying to invent things that will help you reach your goal. So this is what happened when we worked on that problem. So this was with two other fellow students of mine. This did not involve my supervisor. So we had defined this problem and found out techniques to solve it ourselves. So this actually impressed Michael Green a lot.
Mm.
So and then he went out of his way to make sure that I got a fellowship in Gonville and Keys, which was the same college where Stephen Hawking was associated
Was
with. And
nice.
so that actually was the second level, and the second level was even harder than doing a PhD, because in the second level, it's essentially you have to do something sort of, it's an opportunity to do something groundbreaking. And if you manage to solve it, then essentially your career is made.
Absolutely, absolutely.
Yeah.
This is a fabulous kind of, overview of kind of things what you kind of did during this phase of your PhD life. Uh, and this already was laying a foundation for you to becoming an academic, or a decision of you of that came later. What was
No,
the
I think I knew from a very early stage that I wanted to be in academia.
okay?
So it was, I think, even when I started my PhD, I knew that I wanted to continue with it.
Continue.
So the thought of having to do something else was too painful to consider something else as a career. I think it's not necessarily a good thing. I would say that it is also tied in with the way that we are brought up, because in India, the conservative way that we are brought up, we are we are sort of subconsciously told that if you took a gap year, or if you actually explored some other line, other direction, then it's in some kind of failure.
Yeah, yeah,
And this is wrong. This is completely wrong. Very successful people, and this is what you learn when you look at the history of the subject, history of science, that
absolutely.
very successful people actually became successful after shifting,
Mm,
uh, after actually thinking about something else in new light. And so, for example, the discovery of the double helix structure in the
yes,
Cavendish labs by Watson and Crick, they were physicists.
exactly.
But because of Bragg's vision, they were encouraged to think about problems in biology and crystal. I mean, these are basically problems in crystallography, but in a very relevant
Delivery.
area. So you require some visionary that actually provides you that environment, that support, that you go and explore this new direction. So I wanted to stay on in academia, continue doing whatever I was doing. It's not necessarily, I wouldn't say that that was the best course forward, but essentially that's how it panned out.
So that lay also a foundation for you to pursue your interest going forward, and
Yeah,
then you moved to Canada, if I'm correct.
that's right. So I did my first postdoc as a fellow of Gonville and Keys College in Cambridge. So I
College,
did three
Cambridge,
years
and
there.
then
And then both my wife and I, we went to Waterloo. So I was at the Perimeter Institute, and she was at the Institute for Quantum Computing. Yeah.
I should mention to the listeners and also to the viewers, uh, Professor Aninda is married to Professor Urbasi Sinha, who also has been on the Pratidwani recently. Um, Fantastic, to receive two physicists actually complementing and doing research in two very interesting and very different areas of research, and it's a fabulous kind of partnership, so to speak. Anita, I would also want to ask this question. I generally ask for to everybody. You know, it's very very clear from the trajectory you had that you could have easily probably become an academic more in most of the places across the world. You still planned and decided to come back to India. What was the motivation behind that? Why?
The
What?
primarily motivation was personal because both my wife, Urvashi's, and my parents were still alive,
Yeah.
and my father wasn't doing well. So my father was ill for a while, and he really wanted me to come back so that I was next to him during his last years. And unfortunately, that didn't happen because I got my job offer from ISC in February in 2010, and he passed away in March. So
Oh,
it was
sorry.
before I could come back and join. But he was very thrilled. He knew that I had decided to come back to India, and he wanted to. It was there, and my father-in-law also was not keeping well, so we just
Yeah.
wanted to
Yeah.
be there during the last few years. Quite sadly, my mother passed away much sooner than what we had expected. So my mother passed away in 2015, and so now we are left with my wife's mother. So it was primarily personal, but although also having said that, I should say that India has had a very rich culture in theoretical physics,
Yeah,
especially in
absolutely.
high energy physics, in string theory. There are lots of very famous people who've come back, done well by being in India. And so, because of the fact that there were these examples, that made the decision to come back
Decision
much
will come
easier.
back. Yeah. Yeah.
It was much harder for my wife in particular because I think as an experimentalist she needed to develop build a lab, and then it required a lot of support and so on, and that was I think a much harder decision. But um, I think in theoretical physics it wasn't really that difficult. I guess I would have been very heavily inclined to come back anyway because
Mm.
the kind of infrastructure that we need is very little. ISC provides a lot of support,
Good.
excellent students, no question about it. I think
Yeah.
you
Yeah.
also have, being
Yeah.
in ISER, you also have encountered these highly motivated students.
Yes.
And
Yes.
so basically, the undergraduates and the int PhD and the PhD students here are the lifeblood. Uh,
Absolutely.
they just are like a family to you. So it's I have been very happy after coming back. So.
Fabulous, fabulous. So before we just go into your current research interest and also the recent work, I just wanted to just grasp the broad lesson what you extracted out of this whole experience until you moved to become an independent researcher. What was your takeaway from that experience? Having also worked with outstanding people and also done very good work, what were the broad kind of learnings what you got from that experience?
One thing definitely which I want to share with youngsters, and this is a suggestion. This was piece of advice that was given to me by Tony Leggett. So Tony Leggett was a frequent visitor to IQC where my wife was working, and he used to lecture on quantum computing. So he was picking up quantum computing at that point of time. And then I asked him, "So, do you have any piece of advice to me?" He said he thought about it for a while, and he said that if an old person says that something cannot be done, don't believe him. And so
Nice.
that's of course I've always maintained that. I tell people I tell my students the same story, and I think that is one of the key things. As a researcher, you have an intuition that this is something interesting, this is something that needs to be addressed. Have convictions and then address it,
Address it.
irrespective of the fact. This is something that I think requires a lot of mental strength and
Mm.
also determination. That don't be aware whether it's a trendy area or not. It's a difficult thing to implement because it's a sort of a vicious cycle. Because as a student, you want a postdoc, As a graduate student, you want a postdoc, so you want to work in a trendy area so that people are interested in your work. And at the same time, you just don't want to keep repeating what others have done.
Understood. Yeah, absolutely.
You don't want to
Absolutely.
keep following trends, so you want to also be in a situation where you're setting your own trend. So it's a vicious cycle. So one has to strike a balance between the two, because one thing that we say is that if what is the point of writing a paper if nobody is going to read it?
Mhm.
So you have to make sure that you're writing something that people are interested in.
Interesting. Absolutely. Very,
Yeah, so
very,
that's,
very
yeah.
nicely put.
One other thing that I should say is that it is important to be in an atmosphere which is intellectually stimulating, because then you will feel like doing interesting work. You will feel driven. Because if you're in a sort of a well and you don't see, if you don't go outside, if you don't actually get exposure to the fact that what is possible, then you won't feel intellectually stimulated. So
Stimulation.
it's
Yes.
absolutely important that you get a faculty position, but also travel around, because it's very unlikely that you're going to be in an atmosphere that duplicates the atmosphere in Cambridge or Harvard or
Yeah.
Princeton or whatever, and that is very difficult. Those places have been around for many, many, many years.
Yes.
Cambridge has been around for 800 years. So duplicating that is not a straightforward job. So that's why it's important that you travel, you interact with people, go to conferences, or even volunteer to visit places that are of interest to you, and sort of be intellectually stimulated.
Wonderful.
Now it
Wonderful.
is, and so now it is much easier because now you have YouTube. Now you have all
You.
these recorded lectures like what you're recording now, and anybody can access it later on. So I think research has changed dramatically. Like in 2010, there were very few resources where we were able to access online lectures. So one was PIRSA, that was maintained
Yeah.
by Perimeter Institute, and the other famous one was maintained by KITP in Santa Barbara.
Yeah.
Uh,
You're right.
and the MIT series actually
Easy.
started a couple of years later,
Absolutely right.
1 year
Absolutely right.
later, something like that. Yeah. So I would say that just be aware that there are lots of good places, but uh, don't expect that you'll be surrounded with Stephen Hawking, Michael Green, Gibbons, and Peter Littlewood, and whatever. I mean, this is not going to happen easily.
Fabulous, fabulous. There's a lot of things to actually, unbox and go through this. Uh, so now we're going to move towards the contemporary aspect of your research. Define two things. One is, of course, your broad research questions you are interested in. What are the kind of questions you and your group are asking? And specifically, one fabulous result which emerged out of your group, where you have actually kind of come up with a very interesting series for the Pi, and it also has a deep connection to the old Madava series, where Madava series happens to be a special kind of case of a general expansion which you have given, and it also makes the computation of pi much more manageable, both in terms
Uh,
of the rate, yeah, and
yeah,
therefore
so
it'll be great to know
I'll,
about this.
okay, I'll get to pi in a bit,
Uh,
because pi was not the main focus of our
yes,
interest,
yes,
not
yes,
the
yes.
main focus of our people. So there are two important things to be aware of in theoretical physics. And both of them are called standard models. One of them is called the standard model of particle physics. The other one is called the standard model of cosmology. So if you look at the standard model of particle physics, it has got 19 free parameters. So for example, the electron mass is fed in as a parameter and so on. One of the famous parameters is the fine structure constant, 1 over 137.
137. Yes, yes.
And but these are parameters, and it has been a very successful model. It's a model, or you can call it a framework. It has been a very successful model because you open the particle data group handbook. The particle data, if it is printed, is this thick.
Uh,
Got millions of experimental results, and this model with 19 free parameters can explain all of them. Okay. To great successes, people have been struggling to find deviations, to find indications of new physics, and more or less every theoretical physicist who works in this area is convinced that there has to be something more. Okay,
yeah.
so the first thing to ask is what is so special about these 19 free parameters? why do these values take on the values that they do?
Mm.
The standard model of particle physics, as you know, it does not include gravity, but that sort of does not really affect the experimental results because the gravitational coupling is very weak. And
Yeah.
so, at least so far as the standard model of particle physics is concerned, one can think about terrestrial experiments without thinking about gravity.
Yeah. Okay.
But we also know that this is no longer going to be true because using the standard model of particle physics, we don't explain the perihelion precision of Mercury. That's where gravity comes.
Yeah.
So there
Yes.
is competing theory. So there are lots of these questions like why is gravity so weak? Now it's very easy to understand that to explain observations around us, it is vital that gravity has to be weak because otherwise large scale structures cannot form. If gravity was very strong, we'll only have small structures. The solar system would be the size of an atom. So it is vital for whatever reasons for a brain to emerge or for evolution to happen that these large scale structures are there, exist.
Yeah. Yeah.
But there's no fundamental explanation why beyond this anthropic type reasoning. This
Yeah.
anthropic type reasoning appeals to the fact that there has to be these values, otherwise human beings wouldn't be there to think about these values.
This way. Yeah.
That's not very terribly satisfactory explanation.
Yeah. Yeah.
Okay, so you don't have so you're taught in undergraduate or in any course in modern physics that presumably there are four fundamental forces. People have been searching for fifth forces, but with basically no evidence so far.
No worries. Yeah. Yeah.
Okay. And then comes the standard model of cosmology. So standard model of particle physics is trying to explain tiny things. Standard model of cosmology is trying to explain big things. And the standard model of cosmology, in some way of counting, relies on 6 parameters. And of these 6 parameters, the important ones are there is something called the dark energy component. There is something called the dark matter component. And if you actually draw a pie chart, the dark energy and dark matter component contribute to 95% of that cosmic pie chart.
Yeah.
Dark
No.
means we don't understand it. So 95% of the cosmic pie chart or 95% of our own existence, we cannot explain. So in some sense, this is the biggest embarrassment of theoretical physics, that we cannot explain 95% of what we actually see around us, and we cannot explain 19 parameters that we use to fit things. So it is very clear that both these frameworks are incomplete. There has to be something more fundamental out there. And so you want to think about a structure or a framework where you can think about microscopics and macroscopics at the same time. So you want to incorporate gravity and all these fundamental forces together. Now, this was essentially the motivation for pursuing string theory, because string theory provides such a framework. I should tell you that string theory is a particular framework. It has not been successful in explaining any observation so far, but it does provide a framework where we can think about gravity and things that appear to be the forces in the standard model at the same time.
Same time. Okay.
So at least there is a point in the space of theories. We don't know what the other points are, but there is a point where we can talk about gravity and the fundamental forces, the electroweak, strong force and electromagnetic force at the same time. So my research over the last several years has been trying to figure out how to derive the consistency conditions that gives rise to these kind of fundamental forces, which includes gravity.
Nice.
And this is what goes by the name of the Bootstrap program.
Bootstrap. Yeah.
Yeah. So one sort of small success that we had was several years back with Rajesh Gopakumar and a few of my students. We managed to set up the Bootstrap equations in such a way that we were able to calculate critical exponents. So critical exponents, the example that I'm going to give you is that of water. So you know the phase diagram of water has the triple point, and then if you extend the third line, then it actually terminates, and then you start talking about critical opalescence and things like that. So that's a critical point. And you can actually measure things at the critical point. So you can measure the critical exponent associated with specific heat and so on. So the question is, how do we calculate it? And many decades back, Ken Wilson gave us a paradigm how to do these calculations using what is called the epsilon expansion. This is one way of doing it. There are numerical ways of doing the same thing using Monte Carlo techniques. But using quantum field theory techniques, this was one of the ways. But as you know, or as you may have heard, that whenever we try to calculate loops in quantum field theory, typically we encounter infinities, and
Yeah.
we have to make sense of these infinities.
Yeah.
So the way that we had managed to set up these equations is that we could calculate the Wilson-Fisher critical exponents without encountering any infinities, just doing algebra without encountering Feynman diagrams. So that sort of gave us a small piece of encouragement that this way of looking at the equations may shed some light about nature itself. Okay, so
Wonderful.
this is the broad philosophy of the bootstrap. So my more recent work actually tries to address a particular puzzle in string theory, that the bootstrap equations, the way that we had set it up for solving this particular problem for the critical exponents of water, if we try to do the same thing for string theory, then what do the equations look like? So I'm saying for string theory, so let's define string theory as something that has got integer space particle spectrum. So you can think of energies being equidistant spaced and lots of spins and so on. But what equations do we solve to get string theory as an answer? Okay, so that is what the ancients were trying to do. So people in the 1960s and 1970s were actually trying to precisely address this question, except that they didn't have computational power,
Powers. Yeah.
and so they weren't able to frame the equations in a useful way. So this was the motivation for trying to examine this particular question, which led to this new series for pi. So there is an associated problem which can be mathematically explained to anybody who has done a course in mathematical physics. You have this Euler beta function. So the Euler beta function looks like gamma x, gamma y divided by gamma of x plus y. So there are poles in x and y. Okay, but if you open any tables of integrals and products, if you go and do a Google search and ask them to provide you a series representation which makes the poles manifest, they will only give you a series representation which makes either the poles in x or the poles in y manifest, but never
Yeah.
both.
But never both. You're right. You're right.
But the Feynman diagrams actually tells you that both poles should be manifest. So we were asking where is such a representation? Why do mathematicians not know of such a representation? So we invented some tools over the last several years, building on this critical exponent success that we had. So these were all connected. So the research program actually started in some sense in 2015. And we were still trying to work out what the correct way of setting up these equations were, or what the efficient way of setting up these equations were. So then we managed to answer this question, and very sort of two accidents happened. So the first accident that happened was that we had figured out how to make our equations rigorous, but not mathematically as elegant as possible. Out of the blue, last year, a physicist, a statistical physicist by the name of Chao-Ming Song, who's based in the
Yeah.
University of Miami, he, out of the blue, he sent me a draft of a paper, which later got accepted in PRL, which actually showed us or improved on our dispersion relations, what we call dispersion relations.
Yeah.
He found an improvement of our dispersion relations to make certain symmetries fully manifest. And when this paper came, I clicked on the name. I went to Inspire Hep because that's what we do as high energy physicists.
Yeah. Yeah.
So as condensed matter, you probably go to Web of Science or Google
Archive.
Scholar or
Yeah.
something.
Yeah. Yeah.
But the first inclination that we have as high energy physicists is to go to Inspire Hep and search. So I searched for Chao-Ming Song. I saw 2-3 papers. I thought this must be a student, and hence the paper must be wrong. And then then I said, okay, no, this is too sophisticated to be wrong. So I went to Google Scholar. And at Google Scholar, I found out that he's a statistical physicist who writes all these remarkable papers on the connection between statistical physics and, say, the way that COVID spreads, and how to measure impact of a paper, how to predict impact of a paper. So these are all sort of sociological
Yeah. Yeah.
aspects of statistical physics. And he published in Nature and Science and things like that. And I said, okay, so this cannot be dismissed so quickly. So I immediately told my student that we have to examine this. And it turned out that it was correct, except for some small typos or whatever.
Yeah.
And it's correct. And then we realized that this is a very nice thing. In fact, Chao-Ming has now become a very good friend of mine because of
Oh,
this.
okay. Interesting.
I've discussed a lot with him. He's a very nice guy. And he's got this orthogonal way of looking at statistical physics. So it's very, very, very interesting to discuss with him. And so that was one of these coincidences that happened. So then we realized that, together with Arnab, who was there on this
Yeah.
pi paper that you were talking about,
Yeah.
that there is the same kind of techniques could be actually applicable to the first ever amplitude or scattering amplitude that string theory has ever considered, which goes by the name of the Veneziano amplitude, and is essentially the Euler beta function.
Okay. Okay.
And then when you actually extend whatever he did to this, you get a series representation. Okay. So that series representation wasn't completely satisfactory so far as I was concerned, because there was something that was missing. So quantum field theory intuitions told us that there has to be a parameter in that series. A parameter means that for whatever value of the parameter, you should get the same answer.
Mm.
Okay, it essentially has to do with something called field definition, which I don't want to go into because it's a little
Yeah.
technical in
Yeah.
quantum field theory. But so we wanted to find such a representation, and so that was the other key layer that we added to this line of questioning. Where do these parameters come from? So if you remember in the pi series, there is actually a parameter, and so it's an infinite family of
Yeah.
formulas. And that's why,
Yes.
in one end of the formula, you have the Madhava series, in the other end, you have
Mm.
other known series, and then in between, it's completely new.
Mm.
So that's what this pi series looked like. So when we actually wrote up our paper, PRL had changed the format. So PRL actually now has this end matter where you can
Yes.
add an
Yeah.
appendix
Yeah. Appendix.
and
Yeah.
so on. And so I was debating for a while whether I should put this formula for pi into the supplementary material or
Yeah.
into this appendix. And so, if you in our paper, the pi formula appears as the last thing in the this end matter. Okay, and then we had observed that, at the end of this family there is the Madhava series. So Madhava series is sometimes called the Madhava Leibniz series.
Let me see.
And I gave a talk in the West. I won't tell you where because then it'll be figured out. And then somebody was there in the audience again. I won't tell you who because he's very easy to figure out. Who said that? Why do you have to associate Leibniz's name? I mean, Madhava clearly reached there 200 years before Leibniz. So we very cautiously deleted Leibniz's name and called it the Madhava series, and it is a standard terminology that mathematicians use anyway.
Yeah. Yeah.
So anyway, this is historically this is called the Madhava Leibniz series or the Madhava series. And so this was an infinite sequence of formulas, or
Mm.
infinite, uncountably infinite, because you can take lambda to be whatever you want, provided depending on which formula you're looking at, the formula that is there in a paper, the real part of lambda has to be bigger than -1. So lambda could also be complex.
Mm. Mm.
Okay, and you still get a formula for pi.
Fine.
So in fact, you can put lambda equal to pi itself, and you get a weird looking formula where you have pi on the left hand side, pi on the right hand side. And so if you truncate, you basically get an algebraic equation to solve, which will give you pi approximately. So that was the nature of the formula. But the origin of that question was rooted in trying to understand how string theory looks like quantum field theory.
Point of view. Yes. Yes. In fact, this is actually a beautiful kind of description what you gave us. Uh, the fact that you started with a question which had motivations in quantum field theory and also string theory gives a kind of universality of the problems also, right? Because
Yeah.
there's a beautiful kind of connection. Even I kind of partly remember when you gave the talk at ISA Pune, you started off actually defining the problem and mentioning the motivations of why these questions are relevant, and
Right.
also the expansion series is something which you probably always had in your mind, right? Because I going back to the zeta functions and also the gamma functions, what you were mentioning,
Right.
and because as far as I remember, that's where the motivation comes also to look at it from a mathematics viewpoint,
Yeah, I
and
mean, it is quite remarkable because initially we were extremely cautious because this is a function that Euler studied 300 years back.
yeah,
If
yeah.
the mathematicians would have beaten it to death, all possible series representations would have been worked out, and so maybe it is hidden somewhere. Maybe it's somehow you can recombine and you can find some. And then when we put our paper out and it got covered in the press,
Yeah.
people started debating whether the series was new at all in the maths literature. I mean, there are
Mm,
the things called math overflow.
mm,
And they had paid no attention before the paper received any publicity. They had paid no attention to my question, which I had posed in March on Math Stack Exchange. I had asked the same question: Is it known?
Oh, okay, okay.
Can anybody tell me whether this kind of series
Uh,
is so once it got some publicity, people started debating, and they had all
debating.
kinds of things to say. Some people say, we never claimed that this is going to give you the fastest converging series. The fastest converging series, there are these magical formulas that Ramanujan had invented, which arise from modular forms, which still are actually there is no physics interpretation. I think it'll be wonderful if somebody found some physics derivation of those magical formulas. But anyway, so there are loads of these series which converge much faster.
Converse.
Ours was definitely much faster than the Madhava
Faster.
series. Madhava series is one of the slowest converging series representations of pi. So I don't know if anybody tabulated the various standard series representations of pi. The rate of convergence of the Madhava series is abysmally slow. So like to get 10 decimal places, you require like 5 billion terms or something like that.
Terms of- No,
Yeah.
beautiful, beautiful. I should mention to the listeners and also the viewers, I will be linking that particular paper of Anindya's. In fact, it's really worth looking at the paper. It's also very nicely written, at least to whatever extent I was able to kind of grasp and understand. The title is the field theory expansions of string theory amplitudes. The abstract actually is very, very good. To start, the abstract states, motivated by quantum field theory consideration, we present a new representation of Euler beta functions and tree-level string theory amplitude using new two-channel local
Yeah.
crossing symmetry dispersion relation. It also ends very nicely. Our consideration also leads to new QFT-inspired parametric representation of zeta function and pi, which show fast convergence. This is actually, understatement of the kind of
Yeah, because
the,
I guess it.
uh,
Yeah. Okay. I mean, the because of the fact that pi has been so well
well
studied,
studied. Yeah.
Euler beta
No,
function
yes,
pi has been there for whatever series representations dating back from. I think if you look at Wikipedia, I think uh, starting from prehistoric times. I don't even know. I mean,
yeah,
I think 22 by 7. If you will look at it, I mean, there's some. I guess it goes back to Archimedes or some ancient figure who was trying to fit a polygon inside a circle or something like
correct.
that. Some very interesting story like that is there. But because it is there for such a long time, because it has fascinated people for such a long time, we were very cautious because we felt that it might
Mm,
be lurking somewhere in the literature that this formula is known. But so more recently, there are some mathematicians, in particular by a Swedish mathematician by the name of Halmar Rosengren, who has
mm.
found a different derivation of our same formulas. And these kind of this different derivation is in fact targeting mathematicians because in his paper he writes that our paper is difficult to understand for mathematicians. So his the point of his paper is to make the proofs friendly to mathematicians.
Matricious. Okay, very, very fascinating. Very fascinating. Uh, it also probably is a kind of an area of exploration which you did not preempt, right? I
No,
assume.
no, absolutely not. No,
Yeah, yeah, because
this was quite accidental. So this is the second accident. So I was mentioning a bit earlier that there are two accidents. One of them
yeah,
is
yeah,
songs suddenly working in this kind of completely different area.
yes, yeah.
And of course, I always credit him. I asked him later on that why were you actually looking at such technical things? Because these are super technical even for us.
Yeah,
And
yeah.
so he picked up the tools. He wrote a single author paper. So he told me that during the lockdown, he was teaching statistical physics and he was teaching the 3D easing model.
Mm, mm.
Easing, by the way. I should tell your listeners it's pronounced as easy.
Easy. Yeah.
Easing, not easing, easing. So you were teaching the 3D easing model, and then he wanted to sort of summarize what the modern developments were. And then he came across our papers, presumably because they were published in PRL. So
Yeah,
there was a
yeah.
chain of papers that were published in PRL, and it's easy for somebody to read shorter papers. And
Shorter, yeah.
then he felt that the way that we had set up the equations was sort of logically pleasing for him.
Mhm,
He
mhm.
said, "You have good taste." That I keep in my talk in my talks when I talk about this, he had good taste, so he was reading our papers. But the second accident is this Halmar coming up with an alternative proof.
Beautiful.
Because for whatever reasons, people misrepresented our work also on the internet because somebody who I don't want to name said that we were trying to, for want of better word, saffronize our findings.
Uh,
I mean, come on.
uh,
I mean, anybody will know. Go to Wikipedia. The first series representation was written down by Madhava. There's no question
yeah,
about it. This is accepted by Western mathematicians. We were not trying to steal credit or anything
yeah,
else.
yeah.
I mean,
No,
this is,
in fact,
yeah,
I'm very glad you mentioned because see, the notion nowadays, unfortunately, is that people are throwing the baby with the bathwater.
yes,
And you'll have to really give the credit where there is due, and
yeah,
uh,
exactly,
and not actually take it to the other extreme when in that sense
absolutely.
yeah, yeah,
And it's worth finding out more about the Kerala School of Mathematics because
yeah, yeah,
they did a lot of work and it's beautiful. I mean, they were
yeah,
thinking about infinite series and be proud of it. And
absolutely.
why one shouldn't sort of be shy to admit that Madhava reached there first.
Well, first, yeah, exactly. No, no, I totally kind of appreciate the point and also the principle what was mentioned, because there is no kind of there's nothing. This is a scholarly work. If somebody is serious, they should really go and read the work. Maybe
Yes,
that is probably the place where a lot of people miss it. Most of the time, people who would have not gone and really explored a little bit may want to comment on such things. Apart from the political debates, whatever happened, because I think we are in a better space, in the
yes.
space of ideas, so to speak. Yeah, as we conclude, please let us know your kind of broad questions you are kind of going to explore in the coming time, and kind of the thought processes you have in terms of research and education and other things.
Yeah, so the broadly speaking, I think my research direction over the foreseeable future is to sort of take the good aspects of string theory and try to come up with a broader framework. Because I think string theorists will accept the fact that, although it's an interesting framework, you can ask all kinds of interesting questions like black holes and statistical mechanics of black holes and so on. It has failed to capture anything relevant so far as nature is concerned. And rather than actually uh, hide this fact, we should say that there are good aspects. We should take those good aspects and see whether we can build a better framework or not.
Mm, mm. Nice.
Uh, and this stems from the simple fact that to conclude that something works or something does not work, you have to be confident that you have invented the correct mathematics to address that question.
Mm, mm.
And I, for one, am pretty sure that I'm not arrogant to think that I know enough mathematics or we have invented enough mathematics to answer all these questions in their entirety. So, this is one of the things that I hope is going to happen. And so, this is something that I also tell that, there should be more interaction between theorists, mathematicians,
Mm, mm,
and some kind of for lack of better word, some kind of a bullshitting environment has to be created because
mm.
ideas emerge. Promising ideas emerge when you're relaxed, you're having a cup of coffee, and you're bullshitting.
Yeah.
Okay, and this is something that I don't see anywhere happening in India, at least. I would
So,
really,
so important, so important. In fact, majority of the ideas, if you look at it, actually kind of at least have their roots or seeds sowed when you are really informally talking about it in
yes,
in a very relaxed environment. And
exactly.
yeah, I mean, so yeah, that is something I too kind of agree what you're mentioning. And hopefully, yeah, things will evolve, and also kind of so called bootstrapped literally by some of the developments like what Aninda and others have been kind of really pushing forward. I would also be linking one of the recent current science articles which Anantha and
Yeah.
Aninda actually have written, where they have also laid out very beautifully some kind of description of things in terms of the quantum field theory bootstraps. kind of giving the gist of past, present, and future kind of stuff.
Yeah, and also why
And
it is important to sort of not constantly fill one page. What are the deliverables? What are the practical
yeah.
applications of your research? Because if Dirac was asked this question, we wouldn't have invented positron emission
Quite literally.
tomography.
Yeah, absolutely. In fact, the first reference of that current science article is the usefulness of the useless knowledge.
Yes, that's beautiful paper.
That's a
That's
fantastic
nurse.
kind of yeah. It's a beautiful kind of an exposition. So yeah, Aninda, I'm really was delighted to hear a lot of stuff what you had to kind of tell us about, and I'm very sure we'll also have you later on at some point of time to
That'll be
also have
wonderful.
other discussion. And yeah, thank you very much for your time and your thoughts. And you have actually been a very inspiring figure across theoretical physics and also in physics in general, because there's so many students who look up to you also to learn new things, and there are so many fascinating things because even the undergrads and others, we do have a big contingent of students who actually are interested in theoretical physics, and
Right,
this is a great tradition in Indian science.
right.
Instead of actually just telling that we have too many, what we probably should tell is that we should have many more of this kind in various different kind of
Yeah,
forms and other areas, including experimental physics. So
absolutely. Yes.
there's something a lot for us to learn. Yeah,
Yeah, and you're doing a great work organizing these YouTube videos. It's wonderful. I enjoy listening to several of what you do, several things, and I do hope that we'll meet in the near future and we'll
yeah,
able to discuss things, and maybe some new ideas will emerge through those discussions.
absolutely.
Yeah.
Absolutely, absolutely. So, thank you very much for your time and
Thank you,
thoughts.
Pavan.
It has been an absolute pleasure. So, this is Pratidwani, where we try to humanize science. This time with the one and the only Aninda Sinha. Thank you, Aninda.
Thank you very much. Bye bye.